Okay. Thank you, Pierre. Right, so thank you for the invitation. I'm really happy to be here. Today I'm going to present some work which has been done together with Miguel Onorato, Giovanni De Matteis, Andrea Pezzi, Ballerin, and Rondoni. And it's a PRE of 2022, if you want more details. So this is the outline of the talk. So first of all, I'm going to tell you a bit more about what are negative temperature states, for those of you that are not expert on that. And then I will tell you the model that we use, the discrete nonlinear Schödinger model in one dimension. I will briefly mention wave interaction and turbulence theory, and then show you some of our results and conclusions. And hopefully, I will do that all these in half an hour, and then you are not going to be sleeping, and we're going to be ready for the wine reception. Okay. Perfect. So, general recap: how do we define temperatures in physics or in mathematics? So, first thing, in a non-interactive ideal gas, you can think that temperature is proportional to the macroscopic average of the kinetic equation of the gas components. So formally, you can say that the temperature is also only defined at equilibrium, and for a classical gas, the equilibrium means Maxwell-Boltzmann distribution, for example. So at equilibrium, then the energy per particle is proportional to temperature. Then you have Boltzmann constant, 1/2, and n is the number of degree of freedom of your system. So that's the thing that we learned from kinetic theory of gases. More generally, in statistical mechanics, you can think that temperature can be defined this way. So 1 over temperature is the derivative of the entropy versus the energy when you keep fixed all the other thermodynamic constants. Okay, so you can define temperature in this way. Now, usually, entropy is a monotonically growing function versus energy. And so that means that higher energies corresponds to higher temperatures. This is what we normally experience, for example, in the gas in this room. But there are some peculiar systems where this is actually not true. And you can show that the entropy might decrease after reaching a global maximum, for example, in this case. So if you use this definition here, then you can immediately convince yourself that in this range here, then temperatures are positive, because the slope of this curve, the slope of the tangent is positive. But then after that you reach a maximum, where temperature is infinite, you might end up in negative temperature regions. And this is quite instructive because it tells you immediately that negative temperature states, negative temperatures, are actually hotter than positive temperatures, because they're, let's say, on the right-hand side of this maximum. Okay, so you first go to infinite temperatures, and then you can reach negative temperatures. Okay, so how can we think about a very simple system where we can have these type of behavior? Well, for example, you can think about a non-interacting spin chain. So it's even easier than the easy model, because this spin chain is non-interactive. So the spins of these chains and spins are completely independent one to another. Okay. Let's suppose that we couple this system with an external magnetic field having intensity B. Okay, in my cartoon, magnetic field is pointing downwards. So the minimum energy state of the system is where all the spins of our chain will tend to align with the external magnetic field. So this is the case. So if we have n spins, all the arrows are pointing downwards. So you can measure the energy as the number of spins up minus number of spins down times your magnetic field, the intensity of magnetic field. So in this case, the energy is minimal, and you can also, in an easy way, estimate the entropy, because the entropy is related to the number of configuration of your system. So in this case, you only have this configuration here, given that energy. Okay, so the entropy is actually 0 because you have only one configuration. So now let's suppose that we swap one of the spin, for example, the spin of particle number 1. Okay, so pointing upwards. Then clearly the energy is a bit greater than the minimal energy. And the entropy is also greater than 0 because you have n ways let's say, swap one spin in this case, and so S is greater than 0. And now let's suppose that we keep doing this game of swapping another spin, and so on. At some point, we would have swapped all the spins upwards. Clearly, now the energy is maximal, but now the entropy is also again equal to 0 because there is only one configuration in this case. Okay, so I hope that I convinced you that this is a system where somehow the entropy is maximal after a while, and then it decreases again versus the energy. And indeed, I mean, this type of well, in this regime here, where energy are very, very large, you can have a negative temperature, and this has been observed in this really nice experiment of 1950s. Okay, so there are several other systems where you can play this game, and I'm not going to describe that. So let's move onwards to.
When we ask, so what is the configuration that corresponds to negative temperature?
So,
if possible.
So I would say that the maximal, the state of maximal entropy would be the state where you have exactly n divided by 2 spin upwards and n divided by 2 spin downwards. Okay, and then if you then keep swapping, the spins and pointing upwards, then you will increase more and more the energy, but the entropy will start to decrease. So did I answer your question? Yeah. Yes, well, in this case, there is no notion of kinetic energy because there is no interaction between the spin. It's just that in this system you only have potential energy. But yes, I mean, depending on the system or on the mathematical model that you are considering, you might have potential energy, kinetic energy, both, and so on. But let's suppose that you are able mathematically, analytically, to write down the entropy versus the energy, and you find out that the entropy has some maxima. Then somehow you can you have cases where you might have negative temperatures. Yeah. This is just a cartoon, just to explain in a simple way how you can have a negative temperature in a physical system. Okay, so we wanted to see if these negative temperatures can be obtained in this model here called the discrete nonlinear Schödinger equation. So maybe many of you are familiar with the continuous version of this one. So let me guide you through the discrete nonlinear Schödinger equation. So here psi m is the complex amplitude of an oscillator, let's say, at site m, and we have capital M number of oscillators. And the time evolution of this complex amplitude is dictated by this equation here, where you have some local nonlinearity present, where you've got this nu that somehow controls the amplitude of that, can be positive or negative. And then you have this term here that tells you how the interaction of the site M, that tells you how it is the interaction between site M and site M plus 1 and M minus 1, so the nearest neighbor interaction. So this system here has got two conserved quantities, the Hamiltonian that is defined this way, which is the energy, and the total number of particles, or sometimes called wave action, depending on the community that you work with. And this is the local discretization of the continuous one-dimensional nonlinear Schödinger equation. So you can think of writing the Laplacian operator, or if you are in 1D, the second derivative in x, into finite differences, for example, and then you will get this term here divided by, I don't know, delta squared, where delta is the spacing between two neighboring sites. But differently from the nonlinear Schödinger equation in one dimension, this model here is not integrable. Okay. There is an integrable version of this model, which is called Ablovitz-Ladik, but I'm not going to talk about that. Okay, right. And where you can apply this model? Well, it's a relatively good model in the limit of tight binding approximation. So, for example, you can use this model when you have lossless optical waveguide arrays. and essentially each waveguide will be dictated by the complex oscillator psi m. This is also a good model, for example, for some Bose-Einstein condensate in optical traps in one dimension, and might be also a qualitatively good model for photorefractive crystals. I have to say I'm not really an expert on the derivation of this model in this system, but there is a nice book explaining you all the ideas behind how to derive this model for such physical cases. Okay, so what do we do with this discrete nonlinear Schrödinger equation? The standard technique, as Miguel shown this morning, is to rewrite this equation in Fourier space. So we have a discrete system. So what we're going to make are we're going to introduce some discrete Fourier transforms on how to go from the psi m, so the complex value at the m site, to psi hat k, which is the complex amplitude of the kth normal mode, let's say, in that way. So when you apply this, when you go in Fourier space, the equation becomes this one. That will tell you essentially that the normal mode k1 will evolve according to, let's say, its normal angular frequency, omega of k1, where omega of k is the dispersion relation that depends on the mode k. And then you will have the nonlinearity of the model will give you this extra term in here, telling you immediately that the mode k1 will have interaction with the other three modes, k2, k3, and k4. In particular, you have a two mode going into two mode interaction. And this interaction must satisfy something that is like the conservation of linear momentum. But in here, the system is discrete. And so here we have a Kronecker delta that is defined in this way. So k1 plus k2 must be equal to k3 plus k4 mod m, because we have to take into account the fact that we have a discrete system. And so we have what are called the umklapp scattering processes that are actually physical things happening, for example, in a crystal. Okay. So this is what this modified Kronecker delta takes into account. And in here, I'm just showing you, for example, the wave dispersion relation for a system of 16 sites. So you see here that the wave dispersion relation versus the mode as a maximum, and then decays and goes, and then it's periodic under over 2 pi. Okay. So this is the system that we want to play with, and we're going to apply some ideas coming from wave interaction or wave turbulence. So Miguel has mentioned these briefly this morning, but let me try to explain wave turbulence really in a couple of slides. So the idea is that wave turbulence is a sort of statistical mechanics approach to weakly dispersive systems. So waves in optics, plasma, ocean, Bose-Einstein condensate. So you can really try to apply it every time that you have nonlinear dispersive PDEs, or in this case, the equivalent of nonlinear dispersive PDEs, but in the discrete world. And what the wave interaction or turbulence approach will tell you, it will give you a recipe on how to try to understand the long time behavior of the system. So somehow it will tell you, for example, that at large time, only some wave mode or mode interaction process are efficient to spread energy or other conserved quantities in the system. And normally, this will happen on something called the resonant manifold that depends on the type of the system. So the resonant manifold is some kind of relation between the wave modes and the angular frequencies of such modes. So in this particular case, we have 4 wave interactions or 4 mode interactions. So we're going to have 4 modes interacting like that, 2 modes going into other 2 modes, mod 2 pi, in order to take into account for umklapp processes. And the same thing must, and we also need to satisfy this relation on the resonant manifold for the angular frequencies. So where I remind you the dispersion relation is given by this function here. Now, formally, the wave turbulence is derived taking the limit of n going to infinity, so taking the thermodynamic limit. And when you do that, you can describe the long-time behavior of the system, for example, for some quantities, like the wave action density, which is proportional to the spectrum of your system. And in here, we have taken some averages, statistical averages. So it's a theory that requires some statistical averaging. So, for example, the theory will tell you that this wave action density will satisfy this kinetic equation, which is a sort of Boltzmann kinetic equation, a little bit similar for classical gas Boltzmann kinetic equation. So notice that this equation has some delta functions in it. So this is the delta over omegas, so this relation here, and this is the delta over the wave number. So somehow these two deltas, they will tell you that this integrand is non-zero only at this resonant manifold. Okay. Right. What are the beautiful things of this equation? Well, again, this equation has two invariants, so you can demonstrate that the energy, which is now only the linear part of the energy. Oh yes, I haven't said something. So all this equation all this theory is obtained in the limit of weakly nonlinear regime. So that is why the energy now here has only, let's say, the linear energy contribution, because the theory assumes that the energy coming from the nonlinear component is weak compared to the other one. And then it conserves the total number of particles. So these two conserved quantities are, of course, conserved by this kinetic equation. But it also has an important thing. So one can define an entropy function, in this case, the logarithm of nk. And one can show that this entropy is, well, that there's an H theorem for this entropy. So it means that entropy grows monotonically in time. So you go from some dynamics that is time reversible to some dynamics for this nk, which is time irreversible. So there's a particular arrow in time that they will tell you that the system will tend to, for example, equilibrate. And what is the equilibrium of this equation here? Well, one can show that the equilibrium so that dn of d tau is equal to 0 is given when this n of k has this form here, and this is known as the Rayleigh-Jeans distribution, where in here we have some temperature and some chemical potential of the system. Okay. Yeah.
Is it possible to show that the S function is bounded above? It doesn't go above some threshold, like that threshold of the RJ?
I have to say that I'm not sure. I don't know. Or I don't remember for this case. Right. So let's suppose that, for example, we just have a closed system. We start with some initial condition. We let the system evolve. Then, if this kinetic equation is applicable, then what we expect that at some long time behavior, the system will reach this equilibrium here by given by the Rayleigh-Jeans distribution. Okay. But what is nice from this is that if this is the final equilibrium, we can play with the temperature and chemical potential of the system. And I have to say, sometimes, depending on the communities, the chemical potential is defined as positive or as negative. So sometimes if you're used maybe to a plus sign in here, just bear in mind that basically I'm using the negative convention instead of the positive convention. Okay, but what I want to tell you is that because we have, let's say, two parameters to play with, we can, for example, define positive temperature states like this one. So the red one corresponds to temperature equal to 1 and 0 chemical potential. So here what I'm plotting is the distribution of the energy per mode of the system. So a flat line will say all the each mode has the same amount of energy of the other. So energy equipartition corresponds to that. We can, for example, still keep the temperature positive, but also increase or decrease in this convention the negative the chemical potential. So this will be the equilibrium that one would expect. But for example, we could reverse the sign of the chemical potential and also reverse the sign of the temperature, still having a distribution that is positively defined. And this will give, for example, this state here. So this is a state corresponding to negative temperature, where the equilibrium has a peak around, let's say, the highest mode of the system, which are the mode corresponding to k equal to pi. Okay. So we wanted to see somehow if we were able to obtain this kind of states in the discrete nonlinear Schrödinger equation. But yes, I should say that this system is also really nice because you can actually go from the intensive quantities to the extensive quantities of the system. So for example, let's suppose that you know what is the total energy and total particle of the system. You can obtain analytically what is the beta, so 1 over the temperature, gamma, that is mu over the temperature, so it's something proportional to the chemical potential, and the entropy of the system analytically, so given the energy, the initial energy and the initial particle of the system, which are, by the way, conserved in the dynamics. So that means that you can plot, for example, the entropy versus the energy. So you can see that there's a maximum of the entropy, and this region here corresponds to negative temperatures. Or, for example, you can say, in this parameter plot, you can say, well, given some total number of particle n and total energy E, if you are in here, you've got positive temperature. If you're here, you've got negative temperature. So somehow you know exactly where you are in the system, provided that the wave kinetic equation is satisfied. So you're in the weakly nonlinear regime. Okay, so we wanted to see if all this can be obtained numerically. So what we did, we took the discrete nonlinear Schrödinger equation, evolve this in time using a 4th order Runge-Kutta algorithm, and take usually order of 1,000 realizations and average, taking different, the same initial condition of the spectrum but different phases, and then averaging over all these realization to have some statistics that converges. Okay, so what is the spectrum that we started with? It's some kind of, let's say, Gaussian spectrum that is plotted in here in green, which is already picked around the wave number k equal to pi, so the most energetic wave number. And this is because we in order to realize negative temperature, we need to have a very energetic system. Okay. So if we start with this system here and taking 1,000 realizations, different phases corresponding to this wave mode, let the system go, and then do some averages. This is how the spectrum will evolve. So from the green line, it will evolve to this red line here, and then to the blue line here. And in black, we are plotting the Rayleigh-Jeans distribution. So clearly the system will then converge to the negative temperature states, or equilibrate towards the negative temperature states. And we can also measure the entropy, which is given by this quantity here, and you can actually see that the entropy grows in time. And then it will saturate here, so we're almost sure that we reach some final thermal equilibrium. Okay, so this is quite convincing that somehow you can obtain this numerically, and the theory works. And we can also, so I don't want to spend too much time on that, but we can also try to look at how quickly the fluctuations approach, let's say, some kinetic equations that can be written for the fluctuations. So, for example, we can look at the sorry, it shouldn't be the second moment; it should be the 4th moment of these of psi of k, and this is proportional to the fluctuations now, and not to the spectrum. So, and if we call these, for example, lambda k, so one can write down a kinetic equation for the fluctuation. And I'm hiding all the details under the carpet here, but somehow one can check that if the fluctuation follows in time 2 times the square of nk, then the kinetic equation for the fluctuations is always satisfied, provided that nk follows the kinetic equation described well for nk. So somehow we can test how well the fluctuation follow the prediction for their kinetic equations by looking at these by measuring numerically lambda k for a given mode. For example, here we're doing it for the highest energy mode, k equal to pi, and this quantity here that we can also measure. And you can see here that except for a very short time, so 0 is the initial time of the simulation, 40 is in our unit time, where these two quantities somehow they are not they don't overlap, but then after 40 time units, then these two quantities really overlap. So this means that the fluctuations follow the kinetic theory almost immediately. So the kinetic theory for the fluctuation works at much shorter time scales. Just to go back to this time scale here, so 40, what does it mean 40? So 40 here is almost at this time here, so the entropy is still growing quite a lot. Okay, and I think that with that, I probably better conclude. So what are the conclusions? Negative temperatures are possible in the discrete nonlinear Schödinger equation. And this is actually due to the fact that the dispersion relation of this system has an upper bound. And that the fact that this system has two conserved quantities. So we can really play with the chemical potential temperature in order to have still a distribution that is positively defined. One can obtain some analytical relation between the intensive and extensive quantities, which is nice. And then in the end, negative temperatures are really not so exotic because they behave exactly like positive temperatures. Yes, our conclusions are likely to be valid on other dispersive wave systems characterized by four-wave interaction, where the dispersion relation is bounded from above. And with that, I'll thank you.
Thank you very much. Questions?
So I have one question. Is it possible to establish a negative temperature for continuous nonlinear Schödinger?
Well, in this case, so the continuous version in one dimension is
yes,
integrable.
One dimension, of course.
So it's integrable. So all the kinetic...
Yes, integrable. Yes, in such a case, it seems to me that such a situation is absent, right?
Yes.
So everything is connected with a discreteness of your system. Is it so?
Yes. True.
Yes. Okay.
And also in two dimensions, for example, you will have collapses. So
The dispersion relation is not bounded.
And the dispersion relation is not bounded. True. Yes.
Okay.
Yes, please.
Just sorry, on this question of the continuum equation for nonlinear Schrödinger, yes, I mean, the temperature can be negative up to a critical value. These are mathematical proofs. I mean, it's just basically, well, okay, I don't go into details, but that's a mathematical theorem that, the system, I mean, the entropy sort of has a maximum, goes down, but then there's a critical point where you cannot define the equilibrium measure anymore.
Okay, I'll trust you. I don't know the details, so. But
well, that's the nonlinear Schrödinger equation. Yeah, that's Bulgar and and the continuum. I'm talking about the continuum equation. That was the question, right?
But yeah, but continuous there is no kinetic equation.
Matrix elements are zero.
What?
For integrable equation, matrix elements are zero. There is no kinetic equation.
No, I was not talking about the kinetic equation. It was just a question whether you can define anything like negative temperature states for the continuum equation. That's what I was trying to say.
Just not for one.
No, not for one dimension. Yes, okay. No, not for the kinetic. Yeah, okay. It's an equilibrium measure. I mean, okay. Anyway, but the question which I have is actually, I mean, since the kinetic equation is only valid for weak coupling, I mean, did you check how your results depend on the coupling constant or the strength of the nonlinearity? I mean,
no, I would say we didn't do a very extensive study on that. But what is interesting, what I should mention is that so before there was a general conception, as far as I understand, that negative temperature states were somehow related to the emergence of breeders, so of highly nonlinear solutions, let's say. But what we're showing in here is that actually that's not true. So negative temperature states can be realized in quasi non-interacting regimes. Okay, and so somehow I would expect the kinetic equation to fail around, let's say, very high either positive or negative temperature, and not in this regime where negative temperature are approaching zero towards the minus sign. So in this regime here, maybe the kinetic equation will fail because of the nonlinearity. But somehow we explore more the regime in here close to the negative zero temperature limit, and so somehow the nonlinearity was still small, I think. But maybe Miguel, do you want to also to say something?
No,
I think.
Yeah, but what you're saying is correct. I mean, you need weak nonlinearity to increase the nonlinearity of the system. Then you don't get the ranges distribution expected. You don't get it. I mean, I did one simulation and I was not getting the correct answer.
Because it is unstable, right?
Well, because basically the idea is that the energy that is preserved
Here,
quantity, it is not the preserved quantity in the discrete NLS equation, because the
So it's it's this one.
discrete NLS equation, you have the full Hamiltonian, which is well, you haven't written in Fourier space, but the full Hamiltonian is preserved, not just the linear part. So when you start having the nonlinear part that is getting into the game, then the conserved quantity is not anymore the correct one in the kinetic equation. So this is the reason why it fails. So it's the weakly nonlinear system.
Thank you very much. Last question, okay. Okay, last question, yes.
Normally when you have an integrable NLS or DNLS, you're going integral equation along the double equation. But here this equation that you presented, the discrete equation, it's different from the continuous stages in the coincidence of the lattice. Now, when you go to the kinetic equation, the structure of the kinetic equation is determined by the linearity, so the dispersion is the manifold. So I'm surprised that you still have the same kinetic equation, and I would have thought maybe you have the breaking of the integrability would have occurred with a higher order a bit like that.
Yeah. So I think that I see your point. I think maybe this and it's actually a very good point. I think so. What we numerically solve the DNLS equation. But then when we derive the kinetic equation, we take the thermodynamic limit, okay? But still, we keep the discreteness of the system, and so the dispersion relation is not the same dispersion relation as you would have in the continuous case, because in the continuous case here you will just get k squared. But in this case, we're having a different dispersion relation that is bounded from above, I think.
Small k, you cover up with the continuous, and then you go to equation that small k.
No.
Because there are two ways of taking the large box limit, right? You can take the large box limit in such a way that your Fourier space is continuous, and this is what we're doing. Or you can take the large box limit by making the physical space continuous. Okay, so in that case, it's a long way approximation, as you are saying. Okay, but those two things are different. Indeed, if you Taylor expand this omega k
around here,
small k, you get k squared.
You will get k squared.
You get k.
Yeah. So somehow we are continuous in the Fourier space, but still discrete in.
So in your equation, you just concentrate on small k.
Yeah, that's integral.
You will not find
Yeah. Correct.
Okay, thank you very much. Let's thank all the speakers of the afternoon again. thank you, the technical assistants also. Thank you very much. And it's wine time now.
Yeah, there isn't much in there yet. No titles or anything. There's just the two speakers now.